what I started talking about is that there are ansatzes, right? There are efficient ways to represent a wave function such that they don't have this huge dimensionality, and you can still use them to do things. And one of these things that's been very successful is matrix product states. So let's look at a wave function again. Okay, so I can take any wave function and write it as a sum over some set of coefficients that look like this: n1 to nm, n1 to nm. Okay, so m is the number of orbitals I have, and these are occupation numbers, right? So for fermions, there's 0 and 1. And I have to sum up over all of these things, right? And this represents an exponential number of complex numbers. So what I can do is I can come up with Ansatz for this thing. Okay, so why is it exponential? You can think of it as a tensor with many indices. And I can write this tensor with many indices as a product of tensors with, say, one index. So what happens if I say the following? I request that C of n1 to n big M is just a product of things like this. Okay, C1 of n1 times C2 of n2 until Cm of nm. Okay, so let's think about what this is doing for a moment. So first of all, how many numbers do I need to represent this thing? Okay, for each site I have a number for each value of the index. Okay, so C1 can take, this actually means I have C1 0 and C1 1, right? Because the index n1 can take on two values. So this is two numbers, this is two numbers, and I have m of these. So I've gone from 2 to the m numbers to 2 times m numbers. Okay, so this is linear in the system size. Okay, so in terms of scaling, in terms of complexity, this is awesome, right? If I could actually represent any wave function like this, then we wouldn't have a many-body problem. In fact, you realize that this doesn't have to be, right? This is a guess. This is an ansatz. My wave function doesn't have to be represented by this. You can show that for a non-interacting system, there always exists a basis for which this ansatz, which is called the product state, is exact. Okay, for any eigenfunction of the Hamiltonian. If the Hamiltonian is non-interacting, you can represent it as a product state. In general, for a many-body system, you can't. Okay, so this is just going to be a very weird approximation. Okay, but now what you can do is you can try to improve this thing. So you can take these numbers and promote them to matrices. Okay, so what I'm going to do is to go from this to something like this. C1, N1, and I will give it an index. Let's call it B1. Then I'll have C2, N2, and I'll give it two indices, B1 and B2. And I'll continue this. Eventually I'll have C m minus 1, N m minus 1, B m minus 2, B m, and the final guy is a vector again, Cm nm, Bm. So this has a lot of indices. Okay, it's a little gross, but let's look at what we have here. Okay, so this guy, okay, I have C1, N1. There are two of these. N1 can be 0 or 1. And it has another index, B1. Okay, B1 is an arbitrary index that I introduced. Okay, if it can only take one value, then I go back to this, to a product state. If I allow it to take some number of values, then this guy is a vector. Okay, and let's call the number of values that it's allowed to take right? This thing will be in 1 to big D. Okay, so this is 2 vectors of dimension D. Okay, now the next guy in row has an index B1 and an index B2. Okay, and I forgot to say that we're summing up over all these B indices. Okay, so this is going to be like a vector matrix product. Okay, so this is a D by D matrix for each value of n2. So it's 2 D by D matrices. Okay, and all the ones on the inside are D by D matrices until the one on the end that is a vector of length D again. Okay, so I can count how many, right, how many numbers I have here again. Okay, so each one of these matrices is D squared. Okay, let's ignore for a minute that these are different. Let's say, right, I just have a bunch of matrices of D squared. I have 2 of them for each M, and I have M sites. So I have something like 2M times D squared numbers in order to represent this thing. Okay, so there's still no exponent. This is still all polynomial. Okay, when will this actually become exact? Okay, what do you think has to happen in order for this to be possible to represent any wave function? Okay, so somehow, right, in order for this to be exact, I have to get an exponent back, right? Because the real problem, the exact problem, is exponentially hard. So where will the exponent kick in? What's going to be exponential?
Dimension D maybe?
Yes, okay. So the only free parameter here is this dimension D. Okay, this is called the bond dimension or matrix product state dimension. And if I make this exponentially large, then I can represent any state. Okay? Of course, that will be useless, right? If I make it exponentially large and I already have an exponential number of numbers here, and this whole thing doesn't work. But what we hope is that at least for some kinds of states, we can work with a small d. If we can work with a small d, and that's a good representation of our wave function, and we can operate on it, then this thing is actually useful. And so what it turns out, and this I won't prove to you, but you can find this in the matrix product state DMRG literature, is that states with small d represent states which have finite entanglement. Okay, where entanglement doesn't go very far in space. Okay, so this is nice, okay, because at least for some systems we don't have entanglement between every single part of the system and every other part of the system. Again, in a quantum computer, that's exactly what we want in order to make the best of the computer.
Both sides.
Does it work in what?
If any, so if you have a matrix product state, it definitely has a small entanglement.
That's right.
If you have a state with small entanglement, doesn't mean that this is close to matrix product state.
Yeah. So now it depends on what you mean by small entanglement.
Yeah.
Okay, because entanglement is basis dependent. It's not really a well-defined physical property, right? But if it has a small entanglement in the same basis in which you wrote your matrix product states, right? If it has a finite length entanglement, then that will define the length of, right, the size of the D that you need in order to represent it. So this is nice. You can do a few exact things. So there are a few special models for which you know that entanglement has an exactly finite length. And in those models, you can write an exact matrix product state that solves them. There are like 2 examples like this. Okay, it's not super generic. But there is a quite generic result about 1D systems. So we know... okay, so there's this idea of entanglement entropy. Have you guys heard of entanglement entropy? Okay, so a lot of you have, right? So the idea in general is that if I have a big system A and a small system B, then I can calculate a reduced density matrix for this big system. I can trace out, for the small system, I can trace out the big system. And I can, right, for that reduced density matrix, I can calculate something like rho log rho. Okay, and that's going to be my entanglement entropy. And it tells me in a way how much things in B are entangled with A. And most systems in physics, at least for low energy states, for something near the ground state or thermal states, have some sort of area law for this entanglement. So what we think is that the total amount of entanglement that you have, okay, of entanglement entropy that you have, is related to the area between the systems, not to the volume of the total systems. Okay, so the idea is that if you have systems with a boundary between them, they will be entangled along this boundary. Okay, and you need a special system in order to have them entangled everywhere. Okay, you need to work hard in order to do that. That doesn't normally happen in physics unless you try hard. So systems that have this property have less entanglement. Still, the larger you make the system, right, the more entanglement you will have, right? So if your system is of dimension d, the entanglement entropy will scale like d minus 1. Okay? So still, eventually, even if you have low entanglement entropy, and somehow, in a way that I haven't specified, this entanglement entropy says that you need a small d, okay? D will grow with system size, except in what case?
It's unentangled.
Hmm?
Is a system that is unentangled.
Yeah, if the system is unentangled, then fine. You have a matrix product state, and this works. But, well, most systems will have some entanglement at least, and it will grow with the system size, right? But in what case will it not grow? Okay, D1, right? So if it grows like D minus 1, then in D1 it doesn't grow. So if you have a one-dimensional system, you cut it into two parts, you have entanglement along here. And it doesn't matter how big you make the system, that entanglement is not going to grow. Okay, so there are some logarithmic corrections to this. The system has to be gapped, there are all sorts of conditions, but for some set of systems, this actually seems to work quite well. Okay, so there's a pretty big set of systems which are 1D or close to 1D, for which entanglement entropy doesn't really grow very much as you make the system bigger. And then what happens is that you can settle on a finite D, and with a low order matrix product state, you can do quite a bit of physics. Okay? So this is the general idea. What I would like to try and do is show you, at least a cartoon of how we actually do this, right? So I said that condition 1 for this to be useful is that it's a good, just a second. Condition 1 is that it's a good representation of the state. Condition 2 is that we should be able to work with it efficiently. So how do I actually construct a matrix product state, right? How do I use this? How do I, right, I want to do something with a finite D. How do I set my D? Okay, how do I select this stuff? So I want to show you sort of a procedure of how to do this. Yes?
Did you say that for thermal state we have a CO area law?
For some thermal states, you have an area law, yeah.
Because I thought that like it's a definition that thermal state volume law because of thermodynamics.
Yeah, so again, you can argue about this a little bit, right? You can think about it in many ways, right? So if you think of a state at high temperature, okay, for a generic sort of system, are you going to have entanglement between two pieces of the system that are very far away from each other? Probably not, right? I mean, it's going to be hard to think of a high temperature system that has entanglement across long distances. So actually, if anything, ground states will usually have more entanglements. And there are all sorts of weird systems. Like if you think of a non-equilibrium system that has a current flowing through it, right? And if you're in a real space basis, if a current is going this way, then an electron that used to be here is now here. So, something here is always entangled with something a great distance from it. And this will break down. Okay, so you can think of all sorts of ways to break this, but actually just a thermal state is not such a big deal. And I could talk a little bit about how you represent, right, I'm going to talk only about wave functions. You can do density matrices in these kinds of things, and there are ways to do this. And some of the ways to do this actually come from quantum information. So have you guys heard of this idea of, I forget the name of this, purification? Okay, yeah. So this is something like, Okay, like what quantum information people would call a choice state. So if you take a wave function, make a choice state out of it, you can go to a thermal state out of that. And then it has all the properties of almost of a one-dimensional system. Okay, so again, I don't want to go too far into this, but I do want to show you sort of how this works. Okay, so in order to show, right, I'll do induction again, okay, but I'll try to do something closer to mathematician induction than physicist induction. So let's assume that we have solved the problem for size m, and let's see how we solve it for size m+1. Okay, and if I can do that, then this will probably right, because I can easily solve the problem for size m=4 or something like that. Okay, so what does it mean that I have solved the problem for size m? It means that I have a representation of a Hamiltonian, which I'll write as has m states, and it's in a system with m states. Okay, so an exact Hamiltonian like this is going to be of dimension 4 to the m times 4 to the m, right? But I'm going to assume that this is somehow d by d. Okay, either d is greater than 4 to the m, or I've found some way to compress it in the previous state. Okay, but we'll assume that it's okay for now. Okay, now I'll also need a few more operators. I'll need, for instance, a dagger at site m, okay, for an m-site system. Okay, this also has to be d by d. Okay, I'll need a and a dagger. And I'll need this operator that we used in order to define second quantization operators, okay, which is p m for an m by m system. Okay, so this is just pi m=1 to big M of sigma z. Okay, where these are outer products. So I hope you remember from yesterday that in order to represent a dagger at site M, I need to multiply by sigma z's at all previous sites, okay, to obey fermion commutation relations. Okay, so this will allow me to do that. And that is actually essentially it. Okay, so I need to have a representation which is d by d of all these operators. Okay, now let's assume that I have that. What I will do now is I will add a site to the system. Okay, so to add a site, first of all, I have to have the operators in a system which is of size m+1. Okay, so let's see. A dagger, or I will need a dagger at site M in a system of size m+1. Well, I know what that is, right? It's A or A dagger M in a system of size M times an identity matrix, right? So this is an identity matrix over the Hilbert space of a single site. So it's a 4 by 4 matrix, okay? So this moves me from a size D set of matrices to a size 4D set of matrices, okay? So I'm quadrupling my Hilbert space as I'm doing this. Okay, now I will also need the operators on the new site. So A or A dagger m+1 for an m+1 site system is going to be P, okay? That's why I needed this P, times sigma plus or minus, okay? And of course I can also construct P, right? P m+1, which I'll need for the next step, is PMM times sigma z. Okay, given these operators, these are all the operators I need actually in order to construct my Hamiltonian in the new basis, right? So I'm going to need h m plus 1 m plus 1. Okay, so this is going to be h m m times an identity matrix plus some set of new terms which are functionals of the operators that I know. Okay, these are operators either on my new site, okay, like I could have interaction on my new site, or operators between my new site and the first site in the old system. Yeah.
What if I draw the system size from the left, not from the right?
So you can also do that.
Should I multiply by identity or this?
Yeah, so the order will be reversed. Okay, so you will have something like I times instead of something times I.
Is it okay? Because if I start from, for example, just one side, and then I multiply by identity, so these are no longer fermions.
Yeah, so you have to multiply. If you're multiplying by the left, then instead of I, you will have a sigma z, right? So you have to maintain all these things throughout the calculation. And in a real DMRG calculation, you would actually be doing this from both left and right. Okay, you would, right, eventually what you have is you have a left block and a right block, and you sort of move your active block in between them. Okay, but I mean, okay, let's say it's not so different to do it from the right than it is from the left. I chose to do it from the left because it's a little simpler. Okay.
So from the right, it's okay just to multiply by identity. And so
No, I mean you will have to have a sigma every time.
okay.
Right? If I'm multiplying by the right, then here instead of having a times I would have sigma z times a. Okay. Okay. So yeah. So now I have a 4D by 4D Hamiltonian. Okay, for an m+1 site system, and hopefully I can work with this guy. Okay, so we added one site. We're supposed to be in the limit where we can still do stuff. So now I can diagonalize this Hamiltonian, or maybe I just want the ground state. Okay, so I don't have to do a full diagonalization. I can use sparse matrix tricks to get just the ground state. Okay, so from this thing I can extract some state psi 0. Okay, this is a vector of length 4D. Okay, now what do? I construct. Okay, this is part of the DMRG algorithm. So I construct a sort of pure state density matrix. Okay, so this is a 4D by 4D matrix. Okay, and this will allow me to do what's called targeting the ground state. Okay, what is targeting the ground state? So I want to do now some sort of compression. Okay, I want to reduce my subspace, my Hilbert space size back to D. But I can't do this while maintaining all information. I have to throw some information away. So how do I know which information to throw away? I have to target something. I have to have some goal, some optimization procedure in order to know what I'm throwing away. So, you know, there are several kinds of things you can do, and people do different things in the literature. But one thing you can do is target the ground state. Okay, which is to say, I want to have the best possible representation of the ground state with D vectors. With size D matrices. Okay. So what I will do now is an SVD, singular value decomposition. Okay. Who knows what an SVD is? Okay, good. So you know, if there's like a Landau theoretical minimum for those of us who are what was it? Forced to survive the indignity of suffer the indignity of doing computation instead of real math. Then you know, you should know what a fast Fourier transform is, and you should know what an SVD is, and those are probably top two. Okay, but in this case, it's even less than an SVD. It's almost just diagonalization, right? So what we want is to write this matrix rho as something like this: V dagger A V, where this is a diagonal matrix, and these are unitary matrices. Okay. Now I set this up so that the eigenvalues in this thing are arranged in order, okay, from top to bottom. And now I can actually throw away some of the eigenvalues. Okay, so these are 4D by 4D matrices, but by throwing away some of the columns or rows, I can turn them into 4D by D matrices. Okay. Okay, so I throw away 3/4 in this case of the eigenvalues, the smallest eigenvalues. And this gives me also some sort of numerical procedure to see whether that's important. Okay, so if all those eigenvalues are 10 to minus 15, then I'm totally safe. If some of those eigenvalues are 10 to minus 3, then I should worry. I'm probably not representing my state very well anymore. Okay, so you can have internal to this procedure is some sort of error check that tells you how much data you're throwing away. Okay, sometimes you can get away with throwing away no meaningful data in order to represent the ground state well. Okay, so once I do this, I have these 4D by D matrices. I take them and I apply the same transformation to all my operators. Okay, and they will all be truncated from 4D by 4D to D by D. Okay, and at that point, I've returned to my original starting point, right? But I'm in a system in m+1 electrons, and I have a representation of size D of all the operators that I need in order to go to m+2. Okay, and I can repeat this procedure indefinitely. Okay, so was that more or less clear? Okay, so this is a part of what's called infinite DMRG, right? Infinite system DMRG, IDMRG. The actual DMRG algorithm is a little bit more sophisticated than this. If you do this, you will actually not get a very good representation of your wave function. Okay, this will accumulate errors quite quickly, and there are procedures for correcting it and for procedures for correcting the corrections, and it all gets complicated quickly. I thought about showing you a code. I mean, I have a code for this that is about 150 lines in Python, but I think it's just a little too complicated to, right, especially when I see that you guys are sort of falling asleep here, to do right now. So I said I would forget that. But if you're interested, then talk to me and I can show you how this works. And there are a couple of simple codes available online that you can look at. There are great tutorials about this. Okay, so what I want to do here, okay, is not really to teach you DMRG or matrix product states. Okay, I'm also, right, I've worked with this, but I'm not the biggest expert on this at all. I just want you to sort of see that this exists and see that it's pretty cool, actually. Okay, this idea of compression actually lets you do things that you couldn't possibly do otherwise. And people do really great things with this. So you can do systems with hundreds of sites, even though, you know, your Hilbert space is completely exploding long before that, and you can do that accurately. And people do dynamics with this again. So there is a way to take your propagator, okay, the same propagator that I showed you in exact diagonalization, and apply that efficiently to a matrix product state. Yeah.
Can you comment a little bit on the tensor network generalization?
Okay, so sure. So what DMRG is a matrix product state algorithm, and people like to write it like this. Okay. This is the object that I wrote in the beginning. This is the full wave function, Cn1 to nm. Okay, it has indices 1 to m. Okay, so this is a big multi-dimensional object. And what you do is you write it as a product of small indices, okay, of small matrices with these bonds which are of order d. Okay, so there's some number of d by d matrices which give you an approximation of this huge tensor. Okay, and this works very well in 1D. Okay, this is sort of natural. But then you can say, okay, suppose I now have a two-dimensional system. Okay, what do I do then? So right, it's sort of hard to draw it, but I could draw something like this, right, with a bunch of lines coming in on a grid. And then I could, right, I should really write this as like approximately equals. Right, okay, I'll try to do this. Okay, so what is going on here? Each one of these things is, okay, so it has two bond indices connecting it to other things. Well, this one has two. It has up to 4 bond indices connecting to other things. So it's like a rank 4 tensor instead of a rank 2 matrix, which you have inside of a matrix product state. And you have a product of all these tensors. Okay, and this gives you some representation of a 2D system. Okay, and of course you can continue to do this in 3D. You have more generic things that you can do. So, for instance, this encodes short-range correlations well. But there are matrix product-like, okay, tensor network ansatzes that try to encode long-range correlations to some degree, at least simple long-range correlations, and they're supposed to be good for, say, systems near phase transition, which have divergent correlation lengths, things like this. So there's a whole manifold of methods that can be used for different things. Let's say this is the most this is the most established thing. This works quite well. All these other things are also improving. Okay, but let's say that the biggest things, right, the biggest theorems that make the matrix product state so efficient are the fact that you have this, right, the entanglement doesn't grow in 1D because of the error law, and the fact that you have an exact way of compactifying all these tensors in an efficient way. In higher dimensions and more complicated topologies, you no longer have either of these things, and you lose some of the, let's say, guarantees behind the method. Doesn't mean that it doesn't work. In practice, it doesn't work as well. It does work in many interesting cases. Okay. You guys have a more specific question about this? Yeah, so again, you could easily give a whole course just about this, multiple courses. This is a huge issue. I just wanted to introduce you to the language, and you should be aware that this exists. For instance, if you are interested in doing dynamics for a system that you can write as 1D, then this is probably the right method to do it. Okay. I said that you can write a code for this very easily. If you do start working on this, or even just for fun, I recommend doing that. Okay, this is again, this is more complicated than doing exact diagonalization, which is again more complicated than doing non-interacting systems, but it's not a huge jump. Certainly something that any of you should be able to do, and I think you learn something from it. But just like with exact diagonalization, and to some degree also with non-interacting systems, if you want to do something big, if you really want it to be efficient, then there are libraries out there. Okay, and there are very good codes that people
assume you did so,
yeah,
and received some result.
Yeah.
How do you check that this result is trustable?
Yeah, so you compare against exact diagonalization for a small system. You compare against the non-interacting limit for a big system without interactions. And so then you are basically stuck, right? You compare against yourself. No, there is an internal engine, but right. So as I said, you are making a cutoff every time you truncate the basis, and you can see how far, right, how many eigenvalues you dropped and how big they are. You can do a little bit more than that. You can do the calculation at a few different values of m, and see that you converge to the base. But you know, from experience, it can be very misleading. Okay, so sometimes you get garbage out of this, and it takes work to understand whether you get garbage out of it or not. Okay, and like any non-trivial numerical methods, it's a difficult question to answer in general. You have to be very careful.
I have a recipe for you guys.
Yeah.
If you received something and don't know what is it, send to Professor Guy Cohen. He will figure out.
Yeah. Well, you know, if you do numerics for a while, you get a nose for it. Okay, so I can look at the paper and tell you this is garbage, quite often.
That's exactly
okay,
what I meant.
so, but you have to, if you haven't worked with the method, then it can be hard to judge. It's, okay, so I think that is it. And I think that we should probably have a short break. So that's what I want to say about wave function methods. And again, these are tools that I think everyone should sort of have in their private toolbox. And I'm sure that in many projects you will find a reason to use something like this. But the last talk I want to talk about Green's function methods. And as I remarked earlier, and as James also pointed out today, Green's functions are about limiting yourself to a very small subset of the information that you can know about the system. Okay, and this is bad because you don't know anything, and sometimes you don't have enough information to know which phase you're in. But it is also very economical, and it is also directly related to what can be done in experiments. So this has a lot of advantages, and I wanted to walk you a little bit through diagrammatics, okay, to convince you that it's not very scary and that it's not magical. So I want to do a few things that I think will be very related to James's talks, and maybe we'll give a different view on them. And then I will talk about Monte Carlo, and how we do, especially the Monte Carlo in real time, how we do dynamics with Monte Carlo. Okay, so first of all, let's just write down a Green's function. Okay, so we usually do something like this. Okay, so we want to evaluate the dynamics of this object. Okay, so one thing that I don't really want to do in class, but I would like to encourage you to try as a homework problem, is to try something similar to the approach that we did for single particle density matrices. Okay, so you remember a single particle density matrix is this same object where t equals t prime. And what we saw was that if we try to write down an equation of motion for that thing in a non-interacting system, then we have a sort of closure property. Okay? And the set of single particle density matrices is sort of closed under time propagation. And you can just look at these single particle density matrices. If you have all of them at time t, you can use that to get all of them at time t plus delta t, and you can do dynamics. So something very similar will happen for non-interacting Green's functions. Okay? So how would you go about this? You have to take two time derivatives, one with respect to t and one with respect to t prime. Okay? And if you do this, you will discover that you can essentially do the same thing. You will come across some problems that have to do with the time ordering. Okay? And you should be able to figure them out. But, well, the way that you typically see non-equilibrium Green's functions introduced is even scarier than the way that James introduced Green's functions. Right? They begin by showing you the either 6 or 9 types of Green's functions, depending on which particular formalism you're working on. Then there's a million equations that connect them, and then there are formulas for integrating them on contours. And it is all very clunky, and I don't want to do this because it'll basically scare you away, and it won't give us much. Okay, so you can find all this stuff in the textbooks, and all this stuff is really useful, right? If you actually work with this, then these are things that you should know, but we don't have to get into it directly. Okay, so what I do want to get into is what this Keldysh contour you may have heard of is, and why we need it, and where it comes from, and why it complicates our life a little bit. Okay, so in order to do that, actually, it's enough for me to consider a single time property first. Okay, so let's consider the time dependence of some operator A. Okay, so this is going to be the trace over some initial density matrix, and then you have time propagation with a Hamiltonian A, and you have the other time propagation. Okay, so what does this look like? It looks like we have something here, okay, some element, some wave function which is within the density matrix. It gets propagated in time, then you apply an operator to it, then you propagate it backwards in time, and then you perform the measurement. Okay? And we all understand where this comes from. Okay, this is like elementary quantum mechanics. It's not very complicated, but it does actually have to be dealt with. Okay, so this forward-backwards time propagation is pictorially drawn like this. Okay, you have an operator A here. Here you have time 0. Here you also have time 0. And here you have some final time t. Okay? So why is that useful? It begins to be useful when you're doing perturbation theory. So all of diagrammatics, all these Green's function techniques, they're really about perturbation theory. And what you do at the most basic level is you take one of these guys or both of these guys and you expand them in a Dyson series. Okay, so is there anyone here who has not seen a Dyson series? Okay, so super simple. If I have something like this, okay, I can write this as 1 plus I time integral of, yeah, okay, so I want to do it a little bit differently. Okay, I will say what this is in a moment. Okay, just give me a moment. This is a little bit long. Okay, so this is a series for the interaction picture time propagator. Okay, what is the interaction picture time propagator? Okay, I hope that you remember the interaction picture, but it's something like this. Okay, these guys are interaction picture operators. Okay, that's what this little subscript I says. So what I do is like this. I write my Hamiltonian as H0 plus V. H0 is an easy part, V is my interaction or hard part. Okay. And then V in the interaction picture of T is V propagated with the easy Hamiltonian H0. Okay. So does this ring a bell? Have you guys seen this stuff in textbooks? Okay, so we use this in sort of elementary quantum mechanics as a way to do perturbation theory, sometimes time-dependent perturbation theory. And this is, you know, this is useful for doing the first two orders, but it's really useful because you have this infinite order procedure. Okay, this is what all of diagrammatics is based on. Okay, so this is called a Dyson expansion. And what it allows me to do is it allows me to take this E2IHT, right, and write it as E2, as UT times E to minus IH0T, okay, and then use this series to express everything as a set of diagrams, okay. So essentially when I stick that identity into here, I replace this expression by an infinite series, okay, which has integrals in it of quantities which are either this or my original operator. Okay, so that sounds complicated, okay, and it looks worse if I actually write it out. So let me just look at some term that comes out of that expression, okay? So a generic term is going to have, trace, and I'm going to have vi of time 1, vi of time 2. I have an a here, then I have another vi of time 3. Okay, this one came with a minus I. These two came with a plus I. Okay, so I have to keep track of the number of i's and which direction each one of these guys came from. And then all of these time indices get integrated over. Okay? In what way are they integrated over? Well, these ones are integrated from 0 to t, and these ones are also integrated from 0 to t. Okay? But you have to be careful because in the time ordering, okay, remember that there should be some time ordering in the Green's function. These things have to stay contour ordered. So things which were to the right of the operator have to stay to the right of the operator, and vice versa. Okay, so there is a lot of bookkeeping to be done here. Okay, so what we do in order to represent this pictorially is that we use this Keldysh contour. Okay, Keldysh contour is where our interactions appear. So this is going to be T1, T2, and T3. And here we have a vertex, or a VI. Here we have a vertex, and here we have a vertex. Okay, and that represents a particular contribution to our infinite sum, which eventually lets us calculate our time-dependent operator. Okay. Now, these sets of vertices on a time contour are the basic object in a diagrammatic summation. Okay, you have to still get that set of vertex times on a contour and convert that into diagrams. Okay, so again, this is a little bit scary, but it's not insane. What we typically do to make things just easier is we take this contour and compress it into one line. Okay, so it goes from 0 to t back to 0. Okay, just to make the drawing simpler. Then we put a bunch of vertices on it. Okay, so what is a vertex? That's going to depend on your expansion. Okay, so let's do, for instance, an expansion for the Hubbard model and the interaction. Okay, so for Hubbard model and the interaction, right, this is my V. Okay, my Hamiltonian includes H0, which is the non-interacting part, and the interacting part is exactly the many-body interaction. Okay, and this is the guy I expanded. But these guys have a time dependence. Why do they have a time dependence? Because they're in the interaction picture, right? So I have to propagate them under my non-interacting Hamiltonian. Okay, but you remember that we did dynamics under a non-interacting Hamiltonian, and we said that we can evaluate whatever we like very easily. Okay, this is not a quadratic operator, but when it's propagated under a non-interacting Hamiltonian, I can use Wick's theorem to evaluate it. So I have no problem evaluating what this guy is for any time. Okay, that's a classical cost problem. It's a quadratic cost problem. Okay, so I can get all of these guys. Okay, and then essentially at any one of these points, I have to insert the operators with the time dependence that comes with them. Okay, so let's look at this for a minute. Okay, I can break this down. Let's look at just the term for a particular I. Okay, so for a particular I have an A dagger I up, AI, A dagger I down, AI down. So it has 4 operators and a U. Okay, and then when I write down this particular contribution to this horrid sum, right, then it's going to have 4 operators from here, 4 operators from here. I have my A, which may be some number of operators, and another 4 operators from the last vertex. Okay, so this is a 3rd order term. Just from the interactions, it's going to have 12 operators in it. Okay, so I'm going to have, this whole thing is eventually going to be some long string of A daggers and A. Okay, hopefully we have the same number of A's as A daggers, and then it won't be 0. I didn't count. Okay. Now, okay, so that's something that needs to be summed, but remember that we have all possible pairings, right? So at this point we use Wick's theorem, right? We pair them in some way. Okay, and we get a particular diagram. So every diagram is a combination of a set of vertex times and a permutation of the indices. So if you sum over all possible vertex times and all possible permutations of the indices for each possible set of vertex times, then you have this exact sum over all contributions to the perturbation theory. And that's a horrible infinite dimensional integral that you can never actually do. But what we do in diagrammatic Monte Carlo is we sample a finite number of contributions to that integral. Okay, and from that we get an estimate of the full infinite dimensional integral. Okay, and we have this process by the Metropolis algorithm that James mentioned, by which we don't just randomly throw diagrams around. We have an algorithm which is based on random number generation, but which sort of smartly samples what we think is the important part of the configuration space according to some weight. Okay, so that's the general idea. Let's look a little bit about at what these diagrams look like for a Hubbard model. Okay, so what I want to do at this point is, instead of writing extremely long equations with lots of operators in them, I want to draw this as diagrams. Okay, and this is just essentially a representation. Okay, this is notation. Every diagram corresponds 1-to-1 to a term in the horrible series and vice versa. Okay, so this mapping has to be, perfectly clear, otherwise it doesn't work. But that's all it is. Okay, and it's sort of easier for us humans to think about these diagrams than it is to think about long equations with lots of integrals. So the way that we do this is that we take this guy and we represent each one of the operators in it by a little tick. Okay, so I will actually start by doing, let's think about a more generic model for a moment. Okay, so suppose I have Ni, Nj, right, usually over Rij, something like this. This would be a generic Coulomb interaction, right? Something like a Q squared. So this is typically represented in the following way. Okay, you have a line, this is the interaction, and then these ticks at the end represent A dagger I, AI, A dagger J, and AJ. Okay, and this is some term, right? This is some term with 4 operators that appears somewhere in your sum. And then if you want to write a contribution to the Green's function, right, then all of these things have to be paired together. So for instance, you can choose the pairing where these guys are paired with these guys, okay? And that's essentially the only option you have in this case. Okay, assuming, right, that they're of, let's make them of opposite spin. Okay? But you can do other things. So typically we will write a Green's function. We will have one special line that we designate as, the line we're interested in. And then we will have interactions coming out of it. Okay, so we have things like this. We have things like this. We have things like this. Okay, all of these are just terms in this series. Okay, and again, each one of these terms, each one of these diagrams correspond to just a particular set of perturbation times and you know, the operators that come out of that. Okay, so this is sort of the generic diagrammatics that you usually see in textbooks, but it's actually more complicated than the diagrams that James was showing for the Hubbard model, right? Because as he mentioned, what you do in the Hubbard model is you compress this guy onto a single point. Okay, why is that? Because I is always equal to j. So you have ni up, ni down. So you actually have fewer terms appearing in the series for the Hubbard model. You don't have this term, for instance. Okay, that diagram, which is called the Fock diagram, cannot exist. You do have something which is like the You do have something which is like this diagram, which is called the Hartree or tadpole diagram. Okay, it looks like this. Okay, and you've seen this diagram in James's stuff. And you can also have diagrams which are like this. Okay, and you've seen those too. Okay, so each one of these is a particular contribution, and these are diagrams that are specific to the Hubbard model. Okay, they're a little simpler. Okay, so now what are the rules? Okay, so you always have, when you have Feynman diagrams, you have Feynman rules. So the rules tell you which diagrams you're allowed to draw, and how do you translate these diagrams into equations, right? Because eventually you want to sum up numbers. Okay, so essentially the rules tell you, and we can make them a little more specific or less specific, but let's do a simple version of the rules that works. I'm always allowed to put my diagrams on one line. Okay, this line is time, essentially. So I can go from 0 to beta if I'm on the imaginary time axis. I can go from 0 to t back to 0 if I'm on the Keldysh axis. I can actually do both together, right? There's this thing where you start with an imaginary time axis and then you propagate in Keldysh. So there are all sorts of things, but again, this turns out to be bookkeeping. So this is my time contour, whatever that happens to be. On that contour, I can introduce any number of vertices that I like. Okay, any number is fine. Now, the way that I've drawn it is sort of special. What I want to say is that going down are spin down operators, and going up are spin up operators. And this is useful for standard Hubbard model, because you never mix spin up and down operators. Okay, the Hamiltonian conserves the total number of spins for each spin. So really, you can only connect the bottom ones to bottom ones, the top ones to top ones. And you see that you have ones that go left and ones that go right. Okay, so you're only allowed to connect a left one to a right one. Why? Because a left one corresponds to an A dagger and a right one corresponds to an A. Okay, so which diagrams can we draw here? Let's draw one. Okay, this is a legal diagram that I can draw. So because it is a legal diagram, that term will appear in my perturbation series somewhere. Okay, and I have to sum it up. Okay? And you can talk about connected and disconnected diagrams and all sorts of things, well, we don't really need to for that. Okay? So what I do in diagrammatic Monte Carlo, well, again, there are different kinds, different expansions, but in CT int, in the interaction expansion, I would sum up all possible diagrams of this type, and you know, I would sample them and try to get the sum. Okay, so is that more or less clear? More or less, how do you guys feel about this? Okay, more, okay. So now in this language, we can talk about what is DMFT, okay, or a different viewpoint of what is DMFT. So let's look at diagrams that we can build. So any Green's function diagram needs to have some sort of entry point. Okay, I can draw it like this, some sort of exit point on my timeline. Okay, they don't have to be in the beginning or the end, right? And well, this object is just a non-interacting Green's function. Okay, so that's the first, right, the order 0 contribution to the interacting Green's function. Okay, if I want to write an interacting Green's function with these same time indices, then I could do that with a thick line. Okay, and then I would have to add other contributions to this. Okay, so here's a contribution with one vertex. Okay, contributions to the Green's function are only, okay, well, I guess I should introduce this, are only connected diagrams in the sense that, for instance, this is not a contribution to the Green's function. Okay, because this set of vertices, right, this vertex is not connected to my, these are called external vertices. Okay? It's not about where the vertex is, it's about which permutation I chose. Because, for instance, if I put the vertex in the same place and I do this, then that is a legal diagram. Okay? So if I just sum up all diagrams like this, I will get a Green's function. Okay. Now I want to complicate this a little bit. Okay. How do I want to complicate this? Everything here has a site index, okay, which I have to sum over. So the external indices, I and j, are set by which element of the Green's function I want to calculate. Okay, if I want to calculate gij, this has to be on site I, this has to be a dagger I, this has to be aj. The internal indices are summed over because I need to sum the contributions from this type of vertex for all possible sites where that could exist. So this is some k that gets summed over. Okay, so every diagram like this has a set of internal indices that I'm going to sum over, in addition to the time indices. Okay? And now I can talk about classes of diagrams. And in order to define DMFT, I actually have to talk about classes in terms of which sites they sum. Okay? So it's actually easier to do that if I first talk about what a self-energy is in this context. Okay? And this is actually a really nice way to introduce a self-energy because I can show you what the diagram, essentially what a Dyson equation is doing directly in terms of these diagrams. So for this, it's sort of easier to go back to the representation where I draw these in free space. Okay, so it's nice to draw them on a line, but sometimes it's also useful to write that these things don't depend on topology. So I can draw this as a thick line like this. Okay, and that's sometimes useful. Okay, so what is a Dyson equation? Okay, which you showed before, which you saw before today. So it means this, okay? These two terms are the same as these first two lines of this equation, okay? And then, okay, so again, the Green's function is going to have all possible vertices in between. But I'm going to classify them in a particular way. Okay, I'm going to write them all like this. Okay, so actually, you know what? Let's do something first. Let's do the following. Okay, I've written a particular contribution here, okay, to the Green's function. And this particular contribution has a set of repeating elements. Okay, all of these are that, right, the equivalent of the tadpole or Hartree diagram. Okay, but it's repeated many times. And that is somehow inefficient. Okay, I have to sum up 3 diagrams, but in some way they're all the same. So I would like to have a way not to do this, not to do all this work. Okay, I would like to minimize the amount of work that I'm doing. Okay, remember that theorists are very lazy, but also computers, right? You want them to do less work. So okay, and each one of these, by the way, has some index, right? So I'm going to write something like this. Okay. So this circle over here is the self-energy. Okay. And this actually is an integral equation. Okay. Why is it an integral equation? Because remember, we're summing over all internal indices and we're integrating over all time indices. So here and here, I have internal indices. Okay, so I have a double integral here, and this full Green's function is defined in terms of itself. Okay, so I have an integral equation for the Green's function in terms of itself and some unknown object called the self-energy. Okay. Now, what is this self-energy? There are actually 2 things that people call self-energy. There's an improper and a proper self-energy. But let's choose an example, okay, as my first self-energy. Okay, I'll call this the Hartree self-energy. I will choose this object. Okay. So a Green's function begins with an I and a j. Okay. In order to go from a Green's function to a self-energy, I have to be cruel and cut off 2 of its legs. Okay? So the procedure is leg cutting. So if I take this self-energy and insert it into here, okay, what sort of diagrams can I generate? So of course I have this empty diagram, right? How do I get that? Well, all I have to do is take the first term in my expansion. Okay? Now the next term, I can take my G0 here. I can insert my self-energy. And then for this, I'll insert the first term in my expansion again. Okay, this is a contribution from this guy. But at that second stage, I could have also chosen to insert this thing, right? The second term in my expansion. And then I would have gotten this guy. And I can repeat that any number of times, right? And you can see that I get all possible diagrams of this kind. Okay, so diagrams like this are called improper diagrams. And they're easily summed up by some self-energy. Okay? Okay, now I can do a little bit better than that. I can do sigma for self-consistent Hartree. And that's going to be this. Okay, so what's the difference here? Instead of using the bare Green's function here, the non-interacting Green's function, I'm using a full Green's function. Okay? So what this is going to give me is everything I get from the previous expansion, right? But I will also get things like this. Okay, cactus diagrams. Okay, so just by having self-energy like this, I actually get an infinite subset of all possible diagrams, a rather complicated infinite subset that it would take a lot of work to sum over if I were doing them one by one. Okay? So this is, right, what I'm trying to convince you here is that this is a really powerful technique. Okay? By summing up a small number of self-energy terms, you can sum up a huge number of Green's function terms. Okay? And this is one of the reasons why people do this. Another reason, if you're doing this kind of self-energy, okay, if the self-energy is a functional of the full Green's function, okay, then your approximation is called a conserving approximation, and some rules are guaranteed to be obeyed. Okay, so this is a nice property to have, and these sorts of expansions are somewhat better than these sorts of expansions, not just because they have more diagrams, but because they obey more rules sometimes. Okay, and all of these are just the first order thing. Okay, I can go to the next order self-energies, and then I will have many more diagrams. Okay, so I can do sigma second order. I could have this plus this would be the next term in the self-consistent expansion. Okay. Good. Now, I could, of course, continue this to infinite order, and this is only exact if I sum up all possible self-energy diagrams, and that is just as hard as summing up all Green's function terms. Okay, so again, this is somewhat useful as an approximation, and to some degree, we can use it for sampling within Monte Carlo too. This is there are some methods where we use something like self-energies. I'll show you this when we do dynamics. Okay, so now that we have some examples of self-energies, I hope you guys have a better understanding now of what a self-energy is, what it does, why I want to use it. Again, I'm going to complicate things a little bit and add labels here. Right, so what this self-energy should actually be is sum over all sites I of I, right? And this self-energy actually has, in the second order term, this has some I, this has some I and j. Okay, so the first order self-energy is single site. The second order self-energy has two vertices, so it can live on two different sites. Third order self-energies can live on 3 sites and so on. Okay, so the higher order self-energies can live on many sites. Okay, given that, okay, I now have all the language I need to say clearly what is dynamical mean field theory. Okay, dynamical mean field theory in this language means that the self-energy is the sum over all local terms. Okay, so let's write that as an equation. So sigma DMFT is sum over sites I of sigma of site I. What is sigma of site I? It's the exact self-energy containing all possible terms that could possibly exist for which all the indices are I. Okay? So you can see that this is quite powerful in terms of getting the local stuff right. Okay, this is why we say that it's non-perturbative locally for local physics, because really it does contain the full self-energy. But it's still perturbation theory. Okay, this is not the exact self-energy of the whole system, and it only becomes exact in some very strange limit of infinite coordination number. Okay, so DMFT is exact at infinite dimensions. At finite dimensions, it's an approximation. And we can correct that by adding non-local corrections to self-energy. For instance, adding self-energies for nearest neighbors or next nearest neighbors, or for clusters and all these things. Okay? So pictorially, right, this sigma I is this guy plus this guy, okay? Again, where both of these are I, you cannot have I and j being different. And you can put in some higher order terms, right? Like Okay, but everything has to be I. Okay. So it's nice to write this, okay, you can write, okay, I'm going to use the local self-energy, it has all the diagrams. The reason that this is actually useful is that once you have a self-energy which is local, then this is exactly the self-energy that you have in an impurity model. And we have good numerical non-perturbative methods for solving impurity models. So that means that the mapping between the lattice model and the impurity model through DMFT means that you're solving perturbation theory for a local problem, which has a local self-energy, and you're using the solution of that problem to generate the self-energy of the lattice problem. Okay, so this is why this whole thing actually works.